let's get into this FE finite element boundary integral method. Okay. So this is a little bit of revision of our 2D vector FEM. Okay. Not your regular node based FEM, but 2D vector FEM is what was covered in the previous module. And as you know that there are basically 4 steps in your FEM approach. So there's a lot of equations here. Let's just go one by one. What is the first equation telling you, or rather where is it coming from? This is just coming from Maxwell's equation, right? So you have your 2 equations, you move your 1 by epsilon r on one side and again take a curl, so you can replace curl of E by H, and all those constants become k naught squared, you get a mu r H. I have not put the dependence on space, but everything is a function of space. Epsilon r is a function of space, H is a function of space, mu r could also be a function of space, although we won't consider it, and H is of course a function of space. So this entire left hand side I have called it this functional FHR, which in the ideal world I would like to be satisfied exactly at every point in the computational domain. Okay, that is my wish list. Of course, that is not possible. So I say I will do a weighted residual method. I take some testing function, and the average of this residual, the average of this testing function with this functional, this average should be 0. Instead of making, the first equation is simply obtained if I put Tm to be a delta function, right. So I say that is too rigorous, that is not possible. So let us make it into a function with finite support, right. And we have seen what kind of function did we choose for the Tm in our earlier discussion. They were these vector fields that look like this, right. So arrows, arrows, arrows everywhere, right, with the property that they had constant tangential component on one edge and the tangential component on the other edges were 0, right. So those were our very nice basis functions which were derived from the Lagrange polynomials. Okay, so this we remember. So this was step 1. Step 2, then we just plug this guy into this guy and use a little bit of vector calculus. Again, this is just revision. This equation that we get looks big, but it's actually very easy. We call this the weak form of the FEM. Okay. So this is the point where no approximations have been made, no boundary condition has been applied. Yeah. So you have the left hand side is purely over the boundary. So this is your computational domain, capital omega, and the boundary is gamma, right. So that is where your capital omega and gamma come into play. Okay. So this is exact, no boundary conditions. Then we said this is the point of departure, right. This is where we will make a departure, but just to refresh your memory, what did we do to apply the absorbing boundary condition? We did this, right. We said that this del cross Hs for a plane wave we had derived it was exactly equal to jk k hat cross Hs. So it's true for a plane wave going along any direction. On the boundary we said we are going to enforce it along the n hat direction, right. So n hat is the outward normal. So when k hat is equal to n hat, this relation is true for any plane wave, but in general the waves hitting the boundary are not going to be along n hat, they will be along any direction. So that is why it was inexact, hence the approximate symbol. And we had also said that this condition applies only to the scattered field, not the total field. That is why I am writing this as Hs. So in the right hand side of equation 3, what I would do would be to write H as H incident plus H scattered. For the H scattered term, I will replace this, right. So that gives me my non-zero right hand side, and rest of all we have already seen in the FEM module. Okay. So let's see now. Okay. So this is why when I have my object over here, I need to have some air over here. Okay. Right. So how many unknowns are in this problem? What are the number of unknowns in this problem? As many triangles. I mean as many elements. No. As many edges, right? It's going to be equal to number of edges in triangulation of the domain. How, I mean, if you remember, how did you express the unknown field, right? You wrote this as some I is equal to 1 to 3 ui ti, and ti was my known vector field, u's were the unknowns which I wanted to determine, and by choosing these t's to be those first order Whitney elements, these had unit magnitude, unit tangential component along their respective edges. So, I multiply that by an unknown ui, which tells me what is the magnitude of the tangential field, right. So, this is magnitude of tangential fields. Okay. So far, well, I will not call this volume integral because there is no integral equation over here, but this is a volume discretization. It's a volume discretization. Until, I mean, step 1 to 4 are standard FEM, standard FEM with ABC. Okay. So, what we will do is we will not go to step 4, we will stop at step 3 and we will see how we can marry it with boundary integral. Okay. Now, if the number of edges, okay, so I basically the number of unknowns is the number of edges. So, I am going to break this up into two different components. One is the number of interior edges and the number of boundary edges. Okay. So, I am going to say n is the number of interior edges and m is the number of boundary edges. Okay. So, my sparse system, what is the size of my equations? System of equations, my Ax is equal to b, what is the size of A? When I assemble a system of equations using all of these, what is my system, the size of my system of equations? N plus m cross n plus m matrix size. Okay. So, this is as far as your revision of FEM was concerned. Now, the second part is, I mean, look at the title, is finite element and boundary integral. So, next we will see what is the, just revise the boundary integral part. Okay. This is stuff which you have already seen, but just a revision. These two equations that you see over here, they are your familiar extinction theorem, right. So, what was the problem that we had? This was my V2 and this was my V1, right, which had some G1 Green's function and G2 Green's function. Okay. The exciting source was in volume 1, which is why there is an incident field term over here, but not over here. Okay. So, this hopefully is just a revision for you. So, what were the variables over here? Again, this is TM polarization. So, TM is HX, HY, EZ, right, that is my TM. Okay. So, EZ is a scalar, right. So, your EZ is appearing here and here, similarly here and here. Okay. So, now the challenge that we have discussed using these boundary integral equations is that G1 is fine because it is free space, G2 is the problematic guy, right. So, what do we do with problematic guys? We chuck them exactly, right. So, we do not use equation 6, let us for the moment ignore equation 6. Okay. Why? Because it is not practical to use it. So, now let us focus on equation 5, and well, regardless of equation 5 or 6, if you notice, one other calculation that we had done in the module on surface integral was that this gradient of Ez dot n hat, it was proportional to the tangential H field with some constants, and those constants are over here, right, correct. So, this problem has been written as the variables are these scalars, right? Sorry, this is just Ez. These are the variables. I can as well replace this as H tan and Ez. Okay. How many, when I solved, when I for example take equation 5, what will be the first approach that I will do to solve this equation? How do I, what basis will I choose for my variables Ez and H tan? What did we do when we solved it? Pulse basis, right? So, pulse basis is what we used. Exactly, yeah, that's a good, that's exactly the observation we'll use. Here, if we use a pulse basis, then my Ez and H tan, we are both expanding them on a pulse basis. In each discretization of the boundary, it is constant and with some coefficient which I will determine, and 0 everywhere else. That is the basis, right? If you look at the FEM basis functions, they also, if I look at just the boundary edges, it's also like that, right? It has a constant Ui on the boundary and it's 0 everywhere else. So, that similarity is going to be what we will exploit. Okay. So, now the key part is to get rid of this absorbing boundary condition. So, in other words, this step 3 is where we draw the line. Here is where we draw the line. So, what term is it that we have to deal with? This is the term that we have to deal with. Okay. Notice that this equation is consisting only of H. There is no E over there. Okay. But if I want to link it with the boundary integral equations, somehow I should also get an E over there. So, what is your guess as to what to do over here? Can I get a electric field from in the right hand side somehow? Curl of H reminds you of what? Electric field itself, right? So, what I can do is this T cross 1 by epsilon r curl of H, I am just rewriting that term, dot n hat. This is what we have, right. So, curl of H I can replace as j omega naught, j omega epsilon naught, because that 1 by epsilon r is already there, right. So, this will become T cross j omega epsilon naught E dot n hat. Is that approximate or exact? It's exact, right. So far no issues. So, that just becomes, I can take this j omega naught, okay. T is T, E is Ez z hat dot n hat, okay. So, let us take a sample case over here. This is my n hat, my object boundary, right, and I am just looking at one triangle on it. Maybe it is too skew, maybe we can just make it a little better. Okay. This is a triangle on the boundary, and let us say that my T hat is my tangential vector, it goes along the boundary, okay. And which way is my Z hat? Coming out of the board, okay. Now, T hat, and remember this term is only appearing on the boundary, I do not have to think about it on the inside. So, on the boundary, what is the value of T? It is a very simple question. On the boundary, what is the value of capital T? Yeah, it is a trick question. 1, right? That by definition, that is how I constructed it. These capital T, it is 1 along the boundary, 1 or minus 1 depending on the orientation of your boundary and choice of T, right. So, it is mod T is equal to 1 along alright. So, what do you think will happen over here? Can this expression get simplified? So, I have a vector of magnitude 1 along the t hat direction. So, they have a t cross z. T cross z points in which direction? This guy is pointing along t hat. So, t cross z, right hand thumb rule gives you n hat, right? N hat dot n hat 1, right? So, this is actually going to give you plus or minus j omega naught into the value of Ez, okay, that is it. So, this is actually, I mean, we are almost done with the conceptual part of this. What I have done is, my original equation, which was equation 3 here, had H on both sides. Then I just use Maxwell's equations over here to recognize that curl of H is related to electric field, get that electric field in, and realize that this whole thing is going to evaluate to just plus minus j omega naught Ez. Where will the minus sign come from? Right, if t was pointing along minus t hat, it is possible, depending on, what does it depend on? When will it, what determines the direction of t? The node convention, right, the numbering of the nodes, which is done by the CAD software. So, sometime it may be this way, sometime it may be that way, we just have to be consistent. So, that is where I get my term from. Now, if I take this expression over here, it is not just this that I want to integrate it, right. So, if I want to do integral of this guy d over dl, what will this become? I am assuming that my Ez is going to be expanded on a pulse basis, that means Ez is constant along that edge. So, what will survive in this integral? L, the length of the edge, right. So, this is going to be plus minus j omega naught Ez times length. Okay. So, if I use this is, I mean, this is the key of what I am saying, replacing the absorbing boundary condition by a boundary integral. Now, what I have done is this FEM equation over here, equation 3, the left hand side is the entire machinery of FEM. Left hand side is what is going to guarantee a sparse matrix for me, and the right hand side term I am now replacing it in terms of Ez. Okay. Now, you can ask, I could have done this earlier also, right? So far I have not yet invoked boundary integral method. All I did was to recognize Maxwell's equation saying that this term over here can be replaced by E. So why didn't I do this earlier? No, I mean, how can I replace it, meaning Maxwell's equations makes this to be identically true regardless of any approximation. What is the problem here by doing this? I am adding another unknown, right? Then there is nothing known, there is no incident field information coming into it. So, I will just write a set of true equations which are not helpful. Okay. So, but what is going to give us the additional information is going to be the boundary integral part over here. Okay. So, this is sort of step 1. First, we just change the boundary condition term and we notice that I get a Ez over here. Okay. Before we go further, if I take equation 5 over here, how many equations in how many variables will I get? If I take only equation 5, remember I have how many edges on the boundary? M edges on the boundary. Okay, how many unknowns are there? M plus M. Now each boundary edge has an unknown Ez and an unknown H tan, right. So, you have 2m unknowns. At how many points on the boundary are you enforcing equation 5? At the center of each edge, that is what we had done. Yeah. So, n is the number of interior edges. So, you have your triangulation of the scheme and the edge could either be in the interior or on the boundary. So, n is interior, m is boundary. So, that is why my matrix size was n plus m cross n plus m. Yeah, exactly. So, yeah. Okay. So, 2m unknowns over here, but if I take only equation 5, how many equations will I get? M equations, because there are m edges at the center of each I am enforcing this, right. So, I have m equations, okay, which is why this is not alone. If I use equation 5 alone, I cannot solve this. If I add another m equations from 6, then I can solve a 2m cross 2m system of equations, but I am going to stop short over here. Okay. So, now we are in a good position to put this together.